All right, guys. So in this third and final video over discrete random variables, we are going to talk about variance and standard deviation. We're also going to start to talk about what are called continuous random variables and how they are a little bit different from discrete random variables. So first of all, for variance, if x is, let's say, a discrete random variable and mu sub x is the mean for that discrete random variable, then the variation of x, denoted var parentheses x parentheses, is equal to the sum of your observations x sub I minus your mean mu sub x multiplied by their respective probabilities p sub I. Now, when we talk about standard deviation, obviously we know that that's the average distance from the mean. Remember to calculate standard deviation. That is just the square root of variance. So for sigma sub x, so again, notice that standard deviation notation there. But for sigma sub x, it's just equal to the square root of that above formula for variance. So to look at an example of this, let's talk about those two different types of bets that we've seen so far in roulette. Those two bets are the red-black bet as well as the corner bet, which we now should understand that they have the exact same expected value. How do we think their standard deviations are going to compare, though? Let's calculate both and confirm whether or not our answer is correct. So with the red-black model, just as a friendly reminder, the distribution for that was there were three possible outcomes, which were to win $1 or to lose $1. And remember, to lose $1, there were a couple different ways that could happen. So in order to win $1, remember it had to land on either red or black, which gave you an 18 out of 38 probability. Whereas to lose, if it landed on, let's say, the other red or black, you would have an 18 out of 38 chance of that happening. Again, you'd be losing $1 in that case. And last but not least was if it landed on green, because remember there are those two green spaces, then there was a 2 out of 38 chance that you would lose your $1 there. So remember to calculate the mean for a discrete random variable. We take the expected outcome multiplied by its respective probability. In other words, we take 1 multiplied by 18 out of 38, plus a negative 1 multiplied by 18 out of 38, plus another negative 1, this time multiplied by 2 out of 38, and then that will give you the mean of the distribution. So the mean for this first distribution, we would say is negative 0.05. In other words, in a long series of trials, you'd expect to lose about 5 cents every single time you played it. Now remember, we're never going to actually lose 5 cents playing it. That's just the average over a long number of trials. Now, for the corner model, it actually turns out the mean is the same, but the distribution is slightly different. Remember, for the corner model, you win $8 on a $1 bet if you were to land on one of those four spaces. So $8 for 4 out of 38. Whereas you would lose your $1 for any of the other 34 spaces. So you would lose $1, 34 out of 38 probability there. So again, to find the mean for your distribution, we're going to take our expected values, or we're going to find the expected value by taking the expected outcomes multiplied by their probabilities. So we'll take 8 multiplied by 4 out of 38 plus negative 1 multiplied by 34 out of 38, which is going to, again, give you the exact same expected value. So negative 0.05 if we round to that 100th place. Now, thinking about their standard deviations and kind of which one is going to be larger versus which one is smaller. When you're looking at these two, the chances that you win are slightly greater. You're going to win more often playing the red-black model just because your expected probability is 18 out of 38 versus 4 out of 38. Now, in the long run, we're expecting to win about the same. We're still expecting to, well, not necessarily win, but lose 5 cents per average. But kind of looking at these two probabilities and where would we expect to have more frequent success, albeit not long-run success, probably that red-black model. So when we're thinking about standard deviation and which one is going to be more consistent, the red-black model is probably going to be more consistent, where you're going to be roughly closer to kind of 50-50 on your winning and losing, whereas the corner model, where you're going to win less frequently but win more money. So let's confirm that and look at the standard deviations. We're going to actually use our graphing calculator to do that, just to make this go a little bit easier. So in order to calculate these using your graphing calculator, we're going to have to put that data into our stat menu. So we're going to go to stat, press enter for edit. If you do have anything in there, remember to clear out your list, go up to the name of the list and press the clear button. And then let's go ahead and in list 1, write out the expected outcome. So that was to win $1 or to lose $1. And then for list 2, we'll go ahead and type in our probabilities. So 18 out of 38, another 18 out of 38, and then 2 out of 38 for the last. So in order to calculate these, first, let's go ahead and close out of that stat menu. We're going to go back into stat, over to calculate, and this is still one variable statistics. We're still looking at just a single variable here. For our list, we'll keep that as list 1. And since we're dealing with probabilities, we're dealing with their relative frequencies. For frequency list, we're going to go ahead and call that list 2. So in order to do that, we're going to press the second button followed by the 2. That's going to put list 2 in as our frequency list. And then we'll go ahead and press calculate. Notice that that's another way to find the mean, because if you look at that very first decimal value, negative 0.0526 and some change, that is still the mean for our distribution. So the mean of X is that negative 0.05, but now we can also see the standard deviation. So notice that the standard deviation for this red-black model, which I'll go ahead and write here in the notes as well, but our standard deviation for that red-black model is that sigma sub X is equal to 0.9986. We'll just go to 4 decimals for right now. So next, let's see how that compares to our corner model. So we're going to go back into stat, change our options here in edit. We're going to change it to be $8 for the first and then negative $1 for the second. We'll also change our probabilities to be 4 out of 38 and then 34 out of 38 respectively. So here's what our data should look like in the stat menu of our calculator. Once again, we're going to close out of that, go over into calc. This time, ideally, when we hit one of our stats, it should already have it set up as list 1, list 2, and we'll go ahead and press calculate. Notice that once again, for this corner model, we are getting the exact same mean. It's still that negative 0.05, but the standard deviation is much higher. The standard deviation is 2.7620 to 4 decimal places. So notice that the variability for red and black is much less than the corner model, which is what we expected. With red-black, we're going to be winning roughly half the time, whereas for the corner model, we're going to be winning only 4 to 38. So a lot more variability in the corner model than the red-black model. So which one would you rather do? Well, I mean, if you're wanting to, in the long run, be more consistent, you're probably going to pick the red-black. If you're wanting to win some money right away, you might choose the corner model instead because you have a higher chance of winning more, but also you're risking more. Now, are there any dangers to be aware of when we're calculating the mean and standard deviation? Obviously, like anytime we're using our calculator, we need to be careful entering our data, making sure that we are plugging in all of the right numbers into the right places. That would be the only thing to be really careful with. So that pretty much wraps up discrete random variables. In this next section, we're going to start to talk about continuous random variables, which are oftentimes abbreviated CRV. This is where X takes on all of the values in an interval of numbers, and the probability is then described using a density curve. So this is getting back a little bit to what we saw actually in Unit 3 when we talked about the normal distribution. Now, just like in that section, the probability corresponds to the area under the curve. So first of all, what is the difference between discrete random variables and continuous random variables? Well, discrete is going to have set values. You're going to have all of these values, but they are going to be set and restricted to a set of numbers. For example, is it possible to have a shoe size of 8? Yes. Is it possible to have a shoe size of 9? Sure. Is it possible to have a shoe size of 8.5? Yes. Is it possible to have a shoe size of 8.2? And the answer is no. That is what makes this first question a discrete random variable. Shoe sizes are going to be only the whole numbers as well as the half numbers in between. Now, let's consider foot length. With foot length, is it possible to have a foot length of 8 inches? Yes. Is it possible to have a foot length of 9 inches? Yes. Is it possible to have a foot length of 8.5 inches? Sure. Is it also possible to have a foot length of 8.2 inches? And the answer here is yes. For foot length, we are not restricted to just certain numbers. We're able to have all of the numbers in a certain range. That is what makes it a continuous random variable instead. So how many possible foot lengths are there? A lot more. There's a lot of possible foot lengths compared to the shoe sizes. How would we be able to graph those? We would have to use a density curve to be able to do that. Now, when we want to find the probabilities for those, how are we going to do that? We need to find the area under the curve. So finding the area under the curve is going to be how we find our probabilities for a discrete random variable. Now, ideally, if it's normal, then we can just continue to use what we saw in section or in unit 3. Then we can use the normal CDF function of our calculator in order to calculate those. So ideally, that's what's going to happen, is we're going to not only know that it's continuous, but also that it's approximately normal and be able to use normal CDF to find those probabilities. Now, we talked about with discrete random variables, there is a very big difference between the probability of x being less than a, and then it was slightly printed off here in the notes. This should say the probability of x being less than or equal to a. So remember, for discrete, those are two very different values. However, for a continuous random variable, they are the same. The probability that x is less than a will be equal to the probability that x is less than or equal to a. So for continuous random variables, these are going to give you the exact same probability. Remember that that is not the case for discrete. So let's take a look at an example of how to use our continuous random variables. To do so, let's look at the weights of 3-year-old females, which closely follow a normal distribution, that's nice, with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Randomly choose one 3-year-old female, and let's call her weight X. First of all, again, just with some notation stuff here with the way these notes are printed, this should say the mean of X, mu sub X, and over here, S, this should be sigma sub X. So just real quick to make sure we are using the correct notations, I wanted to make sure that those were fixed. So we want to find the probability that a randomly selected 3-year-old female weighs at least 30 pounds. So we're looking for the probability that X is greater than or equal to 30, which, remember, is the same as finding the probability that X is greater than 30 because this is a continuous random variable. In order to calculate that, it does tell us that the weights are normally distributed, which is kind of nice. That means that we can approximate using our normal distribution. Remember, our normal distribution here has a mean of 30.7, and we want to know what is the probability that they are greater than or equal to 30. In other words, if 30 is just a little bit to the left of our mean, we want to find what is the area to the right of it, because remember, it needs to be greater than or equal to or greater than 30. So in order to calculate that, we're going to use our normal CDF button to find our area under the normal curve. For normal CDF, we're going to use 30 as our lower. We'll pick something very large for our upper. And then remember, the mean that they provided to us was 30.7 and standard deviation was 3.6. So using our calculator, let's go ahead and figure out what that would be. We'll go into our distributions menu, choose normal CDF. For lower, we'll make that 30. Remember, upper, we'll just make something very large. And then we'll go ahead and type in our mean as well as our standard deviation. And then we should be able to paste that into our formula. And here is the probability. It looks like the probability that the randomly selected 3-year-old female would weigh at least 30 pounds is 0.5771 if we were to go to 4 decimals, which should also kind of make sense. Remember, 30 is just slightly to the left of the mean 30.7. So it should have been just a little bit larger than 50%. So 57.71% should make sense to us. Next, let's go ahead and find the probability that a randomly selected 3-year-old female weighs between 25 and 35 pounds. So now we want to know between 25 and 35. So the probability that 25 is less than X, which is less than 35. And this is where, guys, it's going to start to become more and more important to make sure that we're using correct probability notation That is going to be something that I will be looking for when we take our Unit 5 test. So once again, our distribution is still the same. Our mean is still 30.7, but now we're looking at a slightly different set of values. We're now looking at from 25, which would be somewhere over here on the left, over to 35, which would be somewhere over here on the right of our mean. And then we're looking at the area in between those two values. So now when we go to type this into our normal CDF, we actually know both our lower and upper values. They are specific values, 25 and 35. Mean and standard deviation still 30.7 and 3.6. So in order to type these in, if you want to go back into the distribution menu, you can. I'm just going to hit second enter to pull up that previous entry. And then I'm just going to change my numbers in here to be 25 and then 35 and delete the extra zeros here so that I don't have to go through the distribution menu again. And then I can go ahead and press calculate to find out that 0.8272 would be that respective probability. Last but not least, let's say we wanted to find the probability that x is less than some value, and we knew that that probability was 0.8. So now we know what the area under the curve is, and it asked us to find the value of k. So again, we know what our distribution looks like, mean of 30.7. Now we know that we are looking for a value k, where the area to the left of it, and I say left of it because notice that it is less than, we know that this area to the left of it is an area of 0.8, and we're looking for what is this value k that would work for. This is where we're going to have to switch from using normal CDF to the inverse norm function of our calculator. Now, inverse norm is set up specifically for areas to the left, so we should be able to just use 0.8 without having to subtract it from 1. And then we'll go ahead and use our mean and standard deviation once again. So 30.7 and 3.6. So we'll go into our distribution menu of our calculator. We'll go ahead and choose inverse norm this time, area being 0.8, and then we'll go ahead and update the mean and standard deviation to our specific values. And we're going to find out that that value would be that k is equal to 33.73. Which would have an area, like it says, of 0.8 to the left. In other words, that would be the 80th percentile. So to kind of think of it in the context of percentiles, that would put you at the 80th percentile at that way. All right, guys, that is it for discrete random variables and a little bit of a glimpse of continuous random variables. Until next time, have a good day.